So we have no agenda today other than to answer questions about either old homework or homework 9. Does anybody have any questions about old homework to start with? Does anybody have any questions about homework 9 to start discussing?
I do have a question if we want to jump into it or if we want to wait.
Okay, maybe wait another 35 seconds to see if more people sign on. But you can be designated first questioner.
Dave, I was going to say I like 19. It says congratulations. End of the class.
Yep. It was a long homework assignment. You deserve something for at least reading the questions to the end. It went on and on and on. Did your version of problem 17 have a big, like, nasty looking, like, spaces in it?
Yep.
I was going to say that. I think
Yeah.
it's missing something too.
Yeah. Okay. Great. That was me being careful when uploading, obviously. So before we forget about anything else, except I'm just a moron. Let's see. Zoom security, allow screen sharing. Screen share. Homework 9. So are you seeing something like solutions to problem 16 and 17?
Yep.
Yeah.
Yep.
So we'll just leave this on the screen for now without giving the solution of problem 17. This is what the question for problem 17 should have read if it had read anything sort of clearly. That it is, we are moving from one locus to a lot of loci and calling V capital A the sum of all the V little a's at all the loci, V capital D the sum of all the V little d's, and V capital E the sum of all the V little e's at all the loci, if you've gotten as far for that to make sense to you. That if you haven't gotten into the homework, what you're going to see is we're going to derive a lot of the key quantitative genetics results first for a single locus, and then very rapidly at the end, we're going to move to multiple loci. And really problem 17 is taking everything we learned at one locus and turning it into the sum over lots of loci. Very, very quickly, effectively. Like that step looks like one step in the whole problem, the whole sort of problem. And so this is the long problem of the homework, so to speak. You end up with something that starts out looking like that for your total variance term. But I will stop sharing right now, and I've promised Brooke that she may start the questioning.
Cool. I think it's hopefully a pretty easy question. It's just for clarity. So I think it starts in question 5. You use the alpha notation,
Yep.
which when looking at the question, it looks like it's just a replacement for, I think, the variance
So
based on, but I was just curious, like why using alpha in this situation?
So let's walk through the problems a little bit. So in problem 2 or 3 rather, in problem 3, I'm going to ask you to find the expected phenotype of someone. I'm going to ask you to actually, to be specific, what I'm asking you to do is pick an allele at random from the population And conditional that that allele is an A1 allele, I'm going to ask you, what is the average phenotype of the person it came from? That's what we're doing in problem 3. And I'm defining that quantity as alpha 1. So alpha 1 is defined as the average phenotype of an individual who has an A1 allele. That if you reach into the population and picked an allele at random, the average phenotype of the person with that allele is alpha 1. And alpha 2 is going to be defined as the average phenotype of a person who, if the randomly picked allele was A2. That's going to be the fundamental definition of those quantities, alpha 1 and alpha 2. We're going to go on to show that for an additive locus, the mean phenotype of an A1 genotype is 2 alpha 1. We're going to show that the mean phenotype for a heterozygote is alpha 1 plus alpha 2. And the mean phenotype for a homozygote of the other type is 2 alpha 2. So alpha will be defined as the average phenotype of a person with an A1 allele, but it will also be shown that the average genotype of an A1 individual is 2 alpha. And we'll then go further and show that the variance can be written in terms of alpha squareds. And ultimately, we're going to start talking about those alphas with the word additive effect. And the square of those things are going to look like additive variances. But we're going to begin with the very concrete definition of alpha as nothing more than the mean phenotype of an individual with an A1 allele, and show how that relates to something we will later call the additive effects, and later the square of that we'll call the additive variances. And ultimately, we will show that the mean phenotype of a relative of someone is a function of the additive variance of those alpha squareds. But we begin with a very concrete definition. They are nothing more than the average phenotype of an individual with that allele. And from there, we are going to get to calling them the additive effects, which is why I gave them the alpha designation, and calling the square of those things the additive variance. Does that make some sense?
Yeah.
Yeah.
And so kind of thinking on that vein, so I don't get tripped up with the other note. So in Gillespie, it's talking about the different average means for, I think, the additive components from the maternal and the paternal genotypes. Yeah.
So,
And I think the averages all basically come out to 0. So I think what's the best way to kind of
you will
keep it
show in
straight?
one of those problems that P alpha 1 plus Q alpha 2 equals 0. You shall show. And that will turn out to be important. That will turn out to be incredibly useful. And in fact, you'll be able to prove that full stop, regardless of whether this is a additive locus or not. P alpha 1 plus Q alpha 2 is 0. End of discussion. For an additive locus, you will be able to show PW11 plus QW1 plus QW22 is 0 also. But that'll only be true for an additive locus. Or W's. X's is what I've called them here. X's.
So
We
the
call them
difference
W's when they're
between,
fitnesses, X's when they're effects. Okay, yep.
yeah, I was going to ask about the X's. So the difference between X and alpha 1, so X11 and alpha 1 is that it's the A1 versus just a single A1 allele?
So we're going to try to maintain the following notation. If it's subscript with 2 things, it's talking about a genotype. So something X11 is the A1 genotype. In this case, the mean phenotype of the A1 genotype. X12 is the mean phenotype of an A1A2 heterozygote, and X22 is the mean phenotype of a A2A2 genotype. The allele alpha, we are ultimately going to start thinking about the contribution of a single allele as alpha. And the subscript associated with alpha will be the subscript associated with the allele it is the mean effect for. So we're going to start ultimately thinking about A1 at the contribution of an A1 allele as being alpha 1, the contribution of an A2 allele being alpha 2. And we'll start calling that contribution the additive contribution of them, but it was also the mean contribution of an A1 allele, but more specifically defined as the mean phenotype of an individual with an A1 allele. And we're going to try to keep separate Arabic letters, A's, B's, whatever, make those associated with alleles, and make Greek letters, alphas, associated with effects or means. So mu will be a mean, alpha will be a mean effect of something. Mu will be at the population level, alpha will be at the allele level.
So hopefully this doesn't sound too confusing, but so the effect of, so the alpha 1, the effect of the A1 allele is also is going to include those individuals that are homozygous for A1 and heterozygous with the A1. Okay, yeah.
Exactly. And in fact, probably in 2-to-1 proportion.
Makes sense.
That the way you're going to get that average is by taking twice the average of A1 individuals with 1 time the average of heterozygotes, or 1 time the average and a half to get it scaled right.
Could we walk through number 4?
For number 4, what is the question?
It is what you mentioned earlier. It's the show that px11 plus qx22 equals 0.
Yep. Would you like some hints with that? Is that what you're asking?
Yeah.
Fair enough. Let's see what I can do. So let me share. Am I sharing screens here? So problem 4 is at the bottom. So in problem 2, you would have shown that if problem 2 went correctly, you would have shown that p squared x11 plus 2pq x12 plus q squared x22 was 0. So if you didn't get that for problem 2, life is going to get much harder. So spend some time on problem 2 showing that p squared x11 plus 2pq x12 plus q squared x22 is 0. With that in your pocket, if you start out writing 0 equals p squared x11 plus 2pq x12 plus q squared x12, that's 0. If you then plug in for x12 the average of x11 plus x22 over 2, that's what happens when it's additive. It's exactly halfway in between. You can then do a little algebra. You'll do a little more algebra. In about 3 or 4 steps, you should get to x11p plus x22q is 0. Just a few algebra steps from starting with the population mean was 0, taking the heterozygous average as being the average of the 2 homozygotes. If that's true, it'll take you 3 steps of algebra to get to the final result we're looking for, assuming you recognize p plus q as 1. And that's all that is.
So sorry if this is, rehashing, but I'm still not quite understanding how we get to that p squared x11 plus 2pq x12
You bet.
Plus q
Sure.
squared x 1 2
Got to
equals
get there.
0.
So let's get there. So can't get these first two problems wrong. Otherwise, the whole homework is going to be impossible. Literally, the homework is going to be impossible if you don't have a zero mean population. So in the first problem, I tell you the phenotypes are Y11, Y12, and Y22. There is nothing you can ever do about that. That's never getting cleaner. That's never getting neater. It is never getting anything other than the mean of the population is going to be the frequency of A1 times its average size plus 2pq times the average value of a heterozygote plus q squared times the average value of the other homozygote. It is never, ever, ever getting any easier than that. That's all there is to it. But in problem 2, I'm going to ask you to create a new random variable x. And x is related to y by subtracting off y's mean. So x11 is just y11 minus the mean of y. x12 is y12 minus the mean of y. x22 is y22 minus the mean of y. Thus, x equals y minus y's mean. It should come as no shock to you right now that the expectation of y is therefore the expectation of x minus x's mean, which is the expectation of x minus x's mean, which means it ought to be 0. So our intuition is that this average ought to be 0, and we can show it that relatively easily. We start with mu x, the average of x is the frequency of A1 individuals times x11 plus the frequency of A1 individuals times x12 plus the frequency of A2 individuals times q squared. We're going to then substitute in for x11, y11 minus y's mean, for x12, y12 minus y's mean, and for y22 and for x22, y22 minus y's mean, which I'm going to then rewrite as p squared y11 plus 2pq y12 plus q squared y22 minus y squared times p squared plus 2pq plus q squared. That number, p squared plus 2pq plus q squared, is the number 1. This here, we just defined in problem 1 as the mean of y. So this total is the mean of y minus the mean of y times number 1, which is 0. So that's going to inform your intuition about quantitative genetics the rest of your life. If you are going to do a quantitative genetics problem, the first thing you do before doing anything else, before thinking in any way, shape, or form, is subtract off the global means. You must get rid of those global means, or chances are you're going to apply a formula wrong somewhere. Every piece of analysis we do is going to have started with the assumption that the mean was 0. And if we ever memorized a formula or utilize a formula, the mean wasn't 0, you're going to run into trouble if you're not super careful. So always subtract off the global mean and start dealing with this other transformed variable that was your original one minus the global mean. When you go back at the end, add back the global mean. But as we know, subtracting a constant doesn't really do anything to most of our key expectations. It changes the mean by a constant factor. It changes the variance not at all. So when we do things about variances, this thing with the global mean removed has all the same variance characteristics. And it'll just make life so much easier for all the formula we do. And you can always do this. There's no reason you can't take any random variable, subtract off the global mean, and now have a new random variable that has mean 0. It's a trick that you should just keep doing as often as you can. Is this clear to everyone? So when you approach this homework, make sure you have a global mean of 0. If you do not, oh my God, are some of these equations going to get bad for you? Don't even hope. Just, I mean, maybe if you're great at this, you'll get through it, but it will be orders of magnitude easier if these means are zero. Other questions?
I have a question about page 6. It's
Number.
really simple. That's when you're finding the expected value of the dominance deviation. Do you want us to leave that in terms of the DIJs or?
Yeah. Well, I want you to find so in problem 6, if you've done problem 6, if everything has gone well up to problem 6, when you find the first moment of the DIJs, you will show there's 0. That the expected value of DIJ is 0. When you go to find the variance of DIJ, you will never, ever be able to simplify that. When you write down the first formula, that's as pretty as it's ever going to get. You'll find 1,000 other forms of it. None of them are any easier or any more intuitive or any better for your life than just the dumbest original formula you started with in the definition. But the mean, hopefully, if the world has gone correctly for you, you'll be able to show is 0.
Okay, so because for that I had just plugged in, D11 times the frequency of A11, and I didn't simplify that, but it should show that we can show that if we substitute in what D11 is, we can show that it's 0. Okay.
So so of course, right? D11 is defined, or define it the other way around. X11 equals 2 alpha 1 equals 2 alpha 1 plus D11, or written the other way around, D11 equals X11 minus 2 alpha. So if you plug in for D11, X11 minus 2 alpha, for X12, for D12, X12 minus alpha 1 plus alpha 2, and for D22, X22 minus 2 alpha, you will have, I think, no trouble showing that 0.
Okay, yeah, because I started calculating the variance without knowing that the mean was 0, and it got really complicated.
And then then it made life really ugly.
Okay.
Yep. And showing the covariance is 0 is impossible.
Okay.
You'll never get through that without getting the mean 0. Or maybe you would, but few will get through that without being able to show the mean is 0.
Thank you.
Yeah. So the expected value of D is 0. The variance in D is never going to be a pretty formula. The additive variance is going to be a pretty formula. The additive expectation is going to be 0. The additive variance is going to be a pretty formula. The dominance variance is not going to be pretty. The covariance at a single locus between the additive and dominance effects are going to be 0. And that's a tricky-ish proof. That's one of the trickier ones you'll do.
What about for E? I kind of have a trouble on, I think it's question 9, bringing in E, where you even start there.
So for problem 9, problem 9 asserts that E's mean is 0, which is fine. And after that, the variance is just the variance in what, like, there's nothing more to learn about it. Just, it has a mean effect of 0 and a variance of something. And there is nothing more to say about it.
Should we know more about like what that variance is, other than just saying?
I think all we're going to say is the total population variance, that its variance is the total population variance minus every other variance we've accounted for. We will think of the environmental variance with the exact same way a statistician would say the error variance. It is the variance of everything else that we have not explicitly identified. And we will often normalize the world so that the whole population is variance 1, and then think of it as the environmental variance is 1 minus all the other accounted for variances. Or simply if population variance is VP, it is VP minus all the other accounted for variances. And you will account for a lot of the variances, By the end of this, you will know exactly what the additive variance is, exactly what the dominance variance is, exactly what the additive by additive variance is, exactly what the additive by dominance variance, the dominance by dominance variance, and all the environmental by genotypic component variances are. You'll know what they are, but the vast majority of the time, you'll just think of them as a sum of a bunch of covariances that I can't measure and hope to God are zero. In some, at least.
I'm a little confused on the covariance aspect.
Yeah.
I think in like 12 through like 17, we go really hard into the covariance. I'm assuming there's a lesson in there that I might be missing because I'm kind of rationalizing covariance. I just don't see how, like for like 7.
Shall we? I'll show you what I'm hoping for you to see. And again, you're looking at some of those questions. Are going, are you trolling me, Dave? Like, what are you doing here? And I'll show you what I was trying to step you through. Okay. So, problem 12. Can you see that at the bottom of my little page here? I ask you to simplify the covariance of X with itself. The covariance of X with X is defined as the expectation of this thing times that minus, well, this is one of the formulas for it, minus the expectation of the first number times the expectation of the second number. When all of them are the same thing, when it's the expectation of X times itself minus the expectation of X times the expectation of X, we get the expectation of X squared minus the expectation of X quantity squared, which you all know is the variance of X. So we just learned the covariance of a random variable with itself is the variance of that random variable. Now in problem 13, I've got 4 random variables, X, Y, W, and Z. And I want to know what the covariance of X plus Y is with W plus Z. All I do is write them down by definition. That is the expectation of this thing times that minus the expectation of the first term times the expectation of the second term. I then multiply crap out and get terms that look like X times Y, X times Z, Y times Y, Y times Z. I then take my expectation of X plus Y, that's the expectation of X, plus the expectation of Y. And I now have these terms to sort of FOIL out. They go on for a while. These terms go on for a while. And then I regroup things to find the covariance of X with Y, the covariance of X with Z, the covariance of Y with W, and the covariance of Y with Z. So what I learned is the covariance of a sum, or in this case, the covariance of one sum with another sum, looks like the sum of all the individual covariances. If I see the sum, I can simply rewrite that as the covariance of X with W, the covariance of X with Z, the covariance of Y with W, the covariance of Y with Z. And if I'd been trolling you a little further, I would have added one more term here so that you would have had a sum of 3 things, and then you'd write those down as all the pairwise covariances, and then I would have made you do it with 4 things and have you write down as all the pairwise covariances of 4 things. Or I might have just had you jump to problem 14, which asks you for the covariance between 2 phenotypes. In this case, I have the phenotype from person 1 and the phenotype from person 2, J. These are person I and person J, who I'm going to assume are related to each other. But I'm going to immediately rewrite person I's phenotype as the additive effect they have from their first allele, the additive effect they have from their second allele, plus the dominance effect at this locus, plus an environmental effect. That's how I'm going to think of person I's phenotype. I'm going to think of person J's phenotype as the additive effect from one of their alleles, the additive effect from their other allele, the dominance effect at this locus, plus the environmental effect. I'm going to keep track of person I versus J with these little I subscripts. And
Dave, I can't
little
see what
ones-
you're looking at there. Can you scroll up a little bit? It's
Yeah.
off my screen. Thanks.
Is it on there now?
Yep.
So these little I subscripts are going to refer to person I. J subscripts are going to refer to person J. The little 1 subscripts below are going to refer to allele 1 versus allele 2. This is just, you only get one dominance effect. So the covariance between these two individuals looks like a sum of an additive effect from one allele, an additive effect from another allele, plus a dominance effect from the locus, plus an environmental effect from person I with person J, which I can therefore, because I just did problem 2 and problem 12 and problem 13, rewrite as the covariance of this with that, 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 the covariance. I can rewrite this as literally 16 covariance terms, which I am going to group together as the first allele in individual 1 with the first allele in individual 2, first allele in 1 with the first allele in 2, all my additive effects, all my dominance effects, all my environmental effects, all my additive by dominance effects, all my additive by environment effects, all my dominance by environment effects. This covariance of these things are 16 individual covariances. And I'm going to make an argument that is going to show that some of these covariance terms are actually variance terms because it is the same allele twice. As we learned here, the covariance of something with itself is a variance, so that if some of these alleles are identical, some of these covariances are not covariances per se, but variances. And we're going to identify which ones are actually variances and finally get through something that says the covariance of one individual with the other looks like the additive variance times something that will be known as the coefficient of relationship, plus R2, the probability they share 2 alleles identical by descent, times the total dominance variance, plus whatever environmental interactions they shared and whatever gene by environment interactions they shared. That's what we're going to get from one locus quantitative genetics. And what we mean by environment interaction and gene by environment interaction, you're going to have an extraordinarily precise definition of as the sum of some of those covariances. That shall make sense to you, hopefully, if we've done this right. And the reason we had you do this is this problem, the sort of key problem in quantitative genetics, uses over and over and over again the covariance between a sum or the individual covariances. And this trick, when we have a single locus and are adding together 4 by 4 things, we will repeat in problem 17, where we're not adding together 4 by 4 things, but a shit ton more. We're not even going to count them. We're just going to label them N's and M's. And we're going to have sums of things up to N, sums of things up to N's, and so forth. That's going to be for the variance. Oh, and then when we do the covariance, it's just going to get even meaner looking. But again, it is just these huge numbers. We're going to decompose a phenotype into a huge number of summed things, and therefore the covariance between two individuals will just look like all of our pairs of covariances, some of which we can order and add up into something interpretable, others of which will be less so. Getting the big picture, guys? So problems, to a first approximation, the idea behind problems 1, 2, 3, 4, 5, 6, 7, 8, 9, really are about finding things that are equal to 0 that you can then drop, and getting in your head an extremely precise definition of what we mean by these variance terms. And then the second half is ultimately going to be about proving the covariance between relatives is a function of those variance terms times values that relate to how the individuals are related to one another. And that's going to give us everything in quantitative genetics, basically. Homework 10 is going to be nothing but applying this over and over again in various ways and sometimes in situations that it weren't even obvious that quantitative genetics applies, but does. And so you should think of homework 9 as helping you understand what all these words mean at a very precise level. And homework 10 is as a bunch of formulas and applications of them that allow you to do useful things like breed cattle, or maybe estimate effects of disease alleles or something. Questions? It'll take you a while to get through this. And if you find that you don't get to some of these things that you think ought to be 0, don't worry about it. Go ahead and assert there's 0 if you need it later. Chances are, other than the dominance variance, which you can never simplify, chances are if you thought this was supposed to be simple or equal to 0, it was. And if you need it to be 0 to make the next problem work, go ahead and force it that way. Other questions? Honestly, if you understand this homework, you will understand quantitative genetics better than the vast majority of your colleagues. Most people, even when they are in this field, have usually a hazy idea of what is meant by additive variance, a hazy idea of what's meant by dominance variance. Even really good people tend to have at best a hazy idea. And, you will see things like the famous LD score regression paper is unbelievably easy to read if you understand what an additive variance is. It's dead stupid. It's in fact so much easier than they think it is. All they've done is written down the additive contribution to variance of this site, and then summed that to the additive contribution of variance from neighboring sites with R squareds bigger than 0, and then taking an average of that. It's things you guys have already proven and should fully understand as very simple ideas, even though the papers seem mystically hard, even to many of your serious colleagues. Questions? Okay. Well, I'll see you next Tuesday. If you send me questions, sort of during the daytime over the weekend, I may come back with some more hints for you. And I will obviously post this recording shortly. And if you, and over the course of this recording, I probably showed the vast majority of my answers. So if you are struggling with where you're supposed to be headed, you may be able to find the right spot in that video and look at what I did and say, huh, this thing's going to 0. Let's see if I can make it match. So feel free. I encourage you to do that if you are banging your head against a wall. Because again, in the end, we want you to understand what all these words mean. And if some of these tricky little bits of showing that this thing is equal to 0 doesn't come easily to you, it's okay to cheat and find the proof of that and move on and let it be 0, so that you don't hurt your understanding while you practice your algebra tricks, if that makes sense. Well, good. See you Tuesday.